Um, Welcome to everybody. I am Lauren Madison. I work in the Center for Energy Efficiency and Renewable Energy at UMass Amherst. As this says, you're going to be muted and you can use the Q&A feature to ask questions throughout the presentation, and then we'll discuss some questions at the end. We will be providing continuing education units to those who need them, and we will send out a link for that along with the slides and recording. Hopefully we'll have all of that ready within about a week. And I just want to let you, those of you who aren't familiar with us, know about the other things we do. We provide training on a variety of energy topics through the Massachusetts Energy Efficiency Partnership. And we also provide technical assistance to a variety of different facility types. So I have some links here where you can go and learn more about what we do. And if you have questions or want to find out about getting some assistance, you can email me, laurenm@umass.edu. And now we can go ahead and get started with the heat pump training. So next slide, please. We are fortunate to have two good presenters with us today who know all about heat pumps, Jason Ganley from Mitsubishi Electric and Adam Camillo from DXS New England, which is the local manufacturer's representative for Daikin. And so I'm going to pass it over to Jason to introduce himself and get started.
Good afternoon, everyone. Just want to start off by thanking you guys for joining us today to learn a little bit more about heat pump technology. Just a quick introduction between myself and Adam. My name is Jason Ganley. I'm one of the members of the commercial sales team for Mitsubishi Electric, located out of the great area of Boston. I've been working with VRF and heat pumps for the past 3 years with Mitsubishi, primarily working with consulting engineers on plan and spec design, and also being their technical support as well. I've also supported architects, general contractors, mechanical contractors, distributors, energy personnel, really anyone that is looking to apply heat pumps in any kind of application and to answer any questions that they might have. So I just want to say, thank you for joining again, and I look forward to talking with you in the slides to come. Adam?
Awesome. Thank you, Jason. And thank you everyone for joining us today again. So to give a quick intro myself, I'm Adam Camillo. I'm with DXS New England. I've been with DXS for almost 4 years now. I originally co-opted with DXS actually back in 2017, and I continued my career here after that. I'm involved in all sorts of things on the VRF side, from selections and early design coordination to full project managing and ordering with contractors as well. So moving on to our agenda here. So we got a pretty packed agenda, a lot of stuff to cover. We're gonna start really at the 10,000 foot level and explain the refrigeration cycle in a little bit. For all of you who are unfamiliar with that, if you are familiar with it, we apologize. We just wanted to take it right from the top. So I'll be going into the first part of that today, and then we're gonna have a short little break, and then we're gonna talk about some heat pump options, identifying heat pump applications, finding contractors, resources. We're gonna take another break, and then Jason and I both have a little case study to go through together as well. So looking at a little sub-agenda of the introduction to heat pumps. So we'll cover how heat pumps work, benefits of heat pumps, the types of heat pumps, refrigerants, and then I'm going to pass it off to Jason to talk about heat pump efficiency and then heat pump maintenance as well. So like I said, we'll take it back to the 10,000 foot level. So if you're somebody very visual, a simple YouTube search for how the refrigerant cycle works or how heat pumps works has all sorts of good short hits. And essentially, we use the refrigeration cycle on almost all HVAC applications. The main purpose of it is to move heat from somewhere to somewhere hotter, which is usually a challenge. So picture your coffee cup, maybe a hot, warm coffee cup on your table in your house. It's going to cool down. It might be sitting at 110 degrees Fahrenheit. The ambient air in your house might be 7 degrees Fahrenheit. So naturally, the heat is going to move from the coffee cup to the ambient air until your coffee cup is the same temperature as your house. So if we want to go the other way around and heat that coffee cup up, we can do a couple things. So we can put it in the microwave, but of course we aren't going to use microwaves in HVAC. We can also use electric resistance heating, which of course is not very efficient, and especially with the price of electricity, that would cost a lot of money. So what we do in a lot of buildings is we burn things. We burn fossil fuels, whether it's natural gas or propane or oil. And because those are still relatively cheap, even though it's not all that efficient, that's still sometimes how things are done. So we could warm our coffee cup up by burning things and generating heat that way, but we could also use a refrigeration cycle and move heat from the ambient in that house into that coffee cup. So another example, picture your refrigerator in your house. Your refrigerator, in theory, is a heat pump. It has a refrigeration cycle. So what your refrigerator does is inside of it, it's trying to maintain around 40 degrees. And as soon as it gets too warm, maybe 41, 42, the compressor kicks on, the refrigeration cycle kicks on, and it's going to move the heat from that 41-degree area to your house, which might be at, again, 70 degrees. So it's moving heat from somewhere to somewhere hotter, which is your house. So essentially a fridge is a heat pump because there's two ways of looking at it. You can think of your fridge as a machine that cools itself down to 40 degrees using the ambient house at 70, but you can also think of your fridge as a heat pump where your fridge heats your house by moving the heat from inside the fridge to the house. So if you were to rip the front doors off your fridge and open your balcony or your front door and point it outside, you just made yourself a custom homemade Airsource heat pump. So that fridge is constantly going to try to cool the outside, and on the back where it rejects the heat, that's going to heat your house. So in theory, again, your fridge is a heat pump. It just depends really how you're looking at it. And that applies for almost any type of refrigeration cycle. Thinking about your car, it has an air conditioner in there. That's a refrigeration cycle. So the compressor uses the energy from the car engine, but that moves heat from inside your car to the outside, even if it's a 95-degree day. So in theory, even in the winter, we could heat our cars using the air conditioner. You could tweak it a little bit, and you could use it to generate heat. However, we have so much excess heat from the engine that we already need to cool, so we just heat our cars that way. But again, the car air conditioner, in theory, could be a heat pump as well. And then now talking about your standard air conditioner, that could be in a hotel, a window shaker like shown here on the bottom right. Those in theory are heat pumps, moving heat from the inside to the outside against a temperature gradient to somewhere warmer. So we're good to advance the slide here. So jumping into the components of any refrigeration cycle. So you've got these 4 components. The numbers here represent the actual refrigeration lines, but looking at the components, we have the condenser, compressor, evaporator, and the expansion device. So number 2 is the refrigerant suction line going into the compressor. Number 3 is a discharge line or the hot gas line that is going outside to your condenser. Number 4 is your liquid line going from your condenser back to your expansion device. And then number 1 is what we call the coil distributor. So to explain a little bit of what this does and how this works and how it is that we can move heat from somewhere to somewhere hotter. Excuse me. So picture yourself, again, to give another example, picture yourself inside your house with a big canister of air at ambient temperature. So if you compress that air a lot, eventually the air in there, it's going to heat up. The energy that it is to get that air compressed, and that canister could get to say 150 degrees Fahrenheit because you've compressed it so much. And then you walk outside and you put it outside. It might be a 95-degree day outside, and that's still much colder than the 150 degrees that your canister of air is at. So if you leave it out there for a while, that canister will eventually cool down to the 95-degree ambient temperature. You can do all sorts of things to make that go faster, like throw a fan on it so the air moves faster across it. You can put some fins around it. So again, you can do some things to make it cool faster. Once you get this high pressure canister of air cooled down to the ambient temperature of 95, if you then bring it back inside and you slowly release it and expand it, you're going to have a cooling effect. So it's going to expand at a temperature much below the 70 degrees that's inside your house. This is similar to an aerosol can being cold. And if you've ever maybe put sunscreen on with an aerosol can, you can feel that a cold sunscreen. That's because it is. That's because when you expand a fluid very quickly, you get that cooling effect. So that right there is essentially how the refrigeration cycle in air source heat pumps work. We will move by compressing air, bringing it outside, letting it cool down, then bringing it back inside. Obviously, we do so continuously using the compressor. So we also don't use air, we use refrigerant. As we like to control the mixture that's in there, the evaporation and condensing points. We want to make sure we don't have any different substances in there that will evaporate and condense at different temperatures. So again, we use refrigerants. And the other big difference is where a lot of the energy exchange comes in is with the condensing and evaporating. So when we take that hot compressed refrigerant outside, we cool it to a point where it actually condenses into a liquid. This is why we call it a condenser outdoors. Then we take that high pressure liquid inside, we expand it, bring it back to low pressure, then it evaporates, and that's where a lot of the cooling effect comes in. So that's what the expansion device is shown here, and that's what that does. So essentially, depending on what way you're looking at it, these are either moving heat from the outside to the inside or the inside to the outside. So the next slide here, we're going to show you two refrigeration cycles that are actually the same, but one of them's in cooling and one of them is in heating. So what you're looking at here, one thing to remember is that compressors only work in one direction, from the suction gas coming in to the discharge gas coming out. So what we don't do if we want to reverse that cycle and start going the other way, we don't just run the compressors backwards. And similar to like a car engine, they always run the same way. If you want to go in reverse, we use a gearbox to switch to reverse. But the engine is always typically spinning in the same way. This is what we do here, which we via the reversing valve, which works as that gearbox. So it can determine in which direction the heat is going. So that's how you can differentiate between a cooling only air conditioner and a heat pump. They both all have those basic four components of a compressor, condenser coil, evaporator coil, and expansion device. The one component that heat pumps have versus cooling only units, whether it's an air conditioner, mini split, VRF, is that reversing valve. So you need that component for that gearbox to be able to switch back and forth between heating inside or cooling inside. So here's an example of a typical house. On the left, in the summer, you have your outdoor unit or your condensing unit rejecting heat. It might be 95 degrees outside, but you've compressed that refrigerant so much, it's at 150 degrees, so it's easily rejecting heat. And because of the exact refrigerant we use, once you start cooling it and it's under pressure, it'll become liquid. And then you bring that back inside and you can evaporate that refrigerant in the low 40s, 42, 43 degrees Fahrenheit. And using that, you're going to cool the air. On the right side, same system, same components, but that reversing valve kicked in, and now we're going the other way. So we're ejecting heat indoors and we're extracting heat from the outside. Now, one of the things that happens when you compare these two scenarios is on the left in the summer, just looking at the temperature differences. So in your house, you're trying to maintain, say, around 70 degrees in the summer. Outdoors, worst case scenario might be 95 degrees in the New England climate. So there's about a 25-degree temperature difference that compressor has to work against. So that's how much it has to compress the refrigerant in order to warm it up enough to be able to reject heat against that big temperature gradient. And then looking on the right side, on a warm winter day, we're still trying to maintain 70 degrees inside. It might be 45 degrees outside on a mild winter day. That's about the same amount of temperature rise as the summer. That's pretty easy to do, not a big deal. So looking when it gets colder and colder outside, you can see how that temperature difference would get bigger and bigger. So thinking about when it's at 20 degrees Fahrenheit, we still need to heat air to make it comfortable 70 degrees in the space. So now you have a 50-degree temperature difference between that 20 degrees outside and 70 degrees in the space that compressor needs to work harder and more electricity needs to go into it. So there's a couple things that happen as it gets colder. One of them, again, is you have to fight that bigger and bigger temperature rise. There's less and less heat in the air as it gets colder. However, until you get to absolute zero, there's always going to be heat in the air. And then 0 degrees might be cold for us as humans, but for the right refrigerant and the refrigerant cycle, there really shouldn't be any issues there. So another example, thinking about your freezer, that little heat pump you have in your refrigerator is able to keep and extract heat from that freezer and heat your house that way. So the one thing that happens as it gets colder is we have a harder time getting heat. You have to put a little bit more power into it, and we tend to get a little bit less heat for every kilowatt of power that we put into it. So we'll actually talk later on something called a COP, which is something on the efficiency side and what might happen as it gets colder. The second thing that happens in the winter, on the right, we are essentially air conditioning the outside to heat the inside. And when we air condition something, If you're maybe currently in your house or an office and it's a hot, humid day, and your house or the office is air conditioned, not only would it be at a nice ambient temperature of maybe 70, 72, 75, but it's also dry. That's because what happens is in the air conditioning system, in the refrigerant cycle, when you evaporate the refrigerant and cool the air, the air is going to hit its dew point, which is what we call it. So it's going to start wringing out some water, and that's how we dehumidify and keep our buildings comfortable. So that's why all these houses and buildings have these condensate drain pans, condensate pumps, condensate lines that are all grabbing this water that's coming off the coils, that's being wrung out of the air, and then they're putting that somewhere. So in an air source heat pump, the same things happens in the winter, but outside. So now we're air conditioning the outside. So if it's 50 degrees outside, but we're running refrigerant through it at 30 degrees and extracting heat from it, we start to cool that air. So eventually it's going to hit its dew point, and we're going to start to condensate water on the outdoor unit, which is fine. There are defensive designs for the water to fall off, but it's always important to think about where that condensate is located, because water is going to come out of the bottom of it. So that's not really an issue until it gets below freezing outside. So if it gets below 32 Fahrenheit, now you're condensating water on your outdoor coil, and that water is going to freeze, of course, when it's below freezing temperatures. But of course, the systems are designed for this. So this is where the term defrost cycle comes in, where the outdoor unit is looking at its condenser coil, and it realizes, because of the amount of heat exchange it's getting, it realizes that it might have ice on it. So therefore, that reversing valve will kick in. It'll reverse the cycle back the other way and put that hot refrigerant through the outdoor coil as quickly as it can to melt and defrost that ice, and then it'll go back to heating the inside. Which means when it gets colder, we have to take that into account. There's defrost cycles that'll happen, but the good news, when it gets really cold, 0 degrees, there's just not that much water left in the air. So the defrost cycles are a bit more rare, but in the 25 to 40 degree Fahrenheit range, outdoor temperature, that's going to be when more of the defrost cycles come into play, when you're looking at an air source heat pump and how much heat you can get. So any manufacturer software properly takes that into account when selecting and sizing the equipment. But again, it's just something else to keep in mind. So moving on here, looking at the benefits of heat pumps. Now, the benefits of heat pumps, again, we touch on the efficiencies a little bit later, but looking back at the 10,000 foot level in cooling, these air source heat pumps tend to use inverter compressors, variable speed compressors. So they tend to be better machines, more efficient than your usual house square, cube, air conditioner outside, or even your regular package rooftop unit and all that. So generally in cooling in the summer, you're not using the heat pump function. You're cooling, but you'll do it much more efficiently. You should be able to use less power, and you should have an advantage there in the summer in cooling. In the winter, though, this is where heat pumps introduce electrification. So that's a concept of if we're trying not to burn things to heat our building, not to burn natural gas or use boilers or furnaces, we need to heat the building somehow. So again, we can use electric resistance heating. That's very expensive and very inefficient to do. That tends to be not all that popular. The other way to do this is we extract heat from somewhere, whether we extract it from the air, which is an air source heat pump, or we extract it from the ground or a lake or water, which is where water source heat pumps come into play, which I'll touch on in a few slides. But that is a concept of, I want to run my building without any fossil fuels. How do I heat the building? So this is where heat pumps come in. So the picture on the right here shows a building that has a PV array. I'll bet it's not too big, but it could be used to feed those 4 little air source heat pumps, which in turn could move heat from the outside to the inside all winter long. So that is one of the steps we take for net zero buildings. Obviously, one of the first steps is to reduce the amount of heat loss, which is what a lot of the passive house standards aim for. And then the air source heat pumps come in and can really handle the rest in terms of the heating and cooling. So looking at the types of heat pumps here, I'm going to compare air source heat pumps to water source heat pumps. Now, I'm sure most of you guys might have heard of both of these, air source and water source. It refers to where is this machine rejecting or injecting its heat. Where is it getting its heat from in the winter, but where is it releasing its heat in the summer? So an air source heat pump, usually it's an outdoor machine. The condenser unit that's outside, that's of course air source. Water source heat pump is a machine that's very, very, very similar, but it's going to get its heat or dump its heat into a water loop. We normally call it a condenser water loop, which comes up as you need somewhere to put the heat or extract the heat from. So many of today's typical Boston condo buildings have water source heat pumps, but they often have a boiler in the building and a cooling tower because at some point in the summer, if everybody's water source heat pump is putting heat into the water can handle a certain amount of heat, but it'll eventually get hot, and we're going to turn on that cooling tower to cool that water down. Or in the winter, if everybody's in heating, everybody's extracting heat from the water loop, eventually the boiler will come on to moderate that water loop temperature. But the other way we use water source heat pumps is that condenser water loop. We then try to dump that heat or get that heat from somewhere else, like the ground or a lake, and that's where your geothermal water source heat pumps come in. And those tend to be called ground source heat pumps as well. Doesn't need to be in the ground. They can be in a lake, but it is a ground source heat pump. Stands for heat pumps that are meant and rated for geothermal temperature ranges. So some manufacturers, they have one model of water source heat pumps you can use for both geothermal and standard water source. Some manufacturers have a specific line of water source heat pumps that they call ground source heat pumps that are meant for geothermal applications. Now, another step on this in the future for these is around handling domestic water via heat pumps, which I'll actually touch on in the next slides. And both air source and water source heat pumps use electricity as their power source. And we'll talk about the possible outputs on the next slide. The efficiency, again, we'll talk about that a little bit later. And then the air source is obviously sensitive to how hot or how cold it is outside. The water source or ground source heat pumps tend to work with water that doesn't get as cold as the outdoor ambient. So we normally design the water loops to not get much colder than around 50 degrees Fahrenheit in a typical geothermal project. So the water source heat pump never really has to go extract heat from air at 0 degrees. It does so from water at 50. So that's why ground source or water source heat pumps will be more efficient, but then you're not done there. You have to move the water around as well. So you really have to look at the entire energy use of a building when comparing the two. And then in terms of capital cost, because of course this comes up a lot. Usually one of the reasons the air source heat pumps are getting so much traction for all electric buildings is because they're usually a lower capital cost. It's typically just an air source condenser on the roof or on the side of the building, refrigerant lines in the building, some fan coils, and that's kind of all you need. Whereas the water source heat pumps need to handle the water side geothermal loops, any wells, pumps, all those additional components. Of course, it's a different story if there's existing infrastructure as well, which we'll touch on a little bit later. So here we're looking again into air source and water source. And you might have heard of air-to-air source heat pumps and air-to-water. So again, air source means it dumps the heat or takes the heat from the air. The other side of the word air-to-air versus air-to-water means what are you trying to heat or cool? So an air-to-air heat pump, like your typical mini split, your typical residential air conditioner, it's going to reject heat or take heat from the outdoor air, outdoor ambient, and that's why the first word is air. But then it's also inside the building. It's trying to heat or cool air. So again, it's air to air. You can do that via distributed systems, ductless or ducted with refrigerant lines. You can do it even with central systems with central vertical air handlers in a closet that could be tied to its own outdoor air to air source heat pump. The air to water, again, it's still outdoors rejecting or extracting heat from the air, but inside the building, it's heating or cooling water. So that's becoming more and more popular as well. There's air source heat pump chillers out there that'll make hot and cold water using the air source heat pump. And usually there's a bit of drop in efficiency because whatever heat you generate, you now have to go through some heat exchanger and transfer the heat over to the water to distribute. And then you need to pump that water around the building as well. But again, there are good reasons to use a hydronic-based system, Airtowater. One of them is on the domestic hot water side. There's more and more technology becoming available to heat or cool, including domestic hot water with an Airsource machine. So they actually do exist residentially for hot water heaters. They exist commercially as well. There's a big challenge there because you're not just trying to heat air inside a building and keep it around 70 degrees. You're trying to make hot water at 140 degrees. So think about that temperature range between the 140 degree water and the 0 degree outdoor ambient. So that's where some of those challenges come in. But again, the technologies are definitely catching up. And then on the water source of water to air, that's your typical water source heat pump. On one end, it's extracting or rejecting heat to a condenser water loop. On the other end, it's cooling or heating air. And usually you have, you might know those are water source heat pumps inside a condo suite that a lot of people have, or in an office building. You have distributed water source heat pumps, and they're all connected to a condenser water line. And then a water-to-water heat pump, those are more common if you're using a geothermal system. We've actually worked on a few school jobs that use water-to-water chillers that essentially reject or inject the heat from a geothermal loop. But on the other end, they heat or cool water, and then from there you can really do whatever you want with it in the building. You can put it through radiators, put it through air handlers, really whatever you need. Then the next level on this is the heat recovery versions of those chillers. They're becoming quite popular as well. You can handle some of the domestic water, and that's because they don't need to go extract heat from 0 degrees outside. They're extracting it from, say, 50 degree geothermal loops. So they tend to be better at generating domestic hot water. So looking at types of air source heat pumps. So if you've ever been in a hotel with that loud machine under your window called a PTAC or a package terminal air conditioner, shown in the top right here, it could be a heat pump. Usually in our colder climates, those are just cooling only, and then the heating's done either via electric heat, or sometimes you even have natural gas distributed to all of them. Some do, but some do come in heat pump functions. And in warmer climates, that's really all they use. You can heat and cool with that PTAC. The condenser sits on the outside, evaporator on the inside, and the compressor and the expansion device are all within that little box you can see there in the top right again. And then the mini split or single split in the bottom left here, which you might have heard of. I'm sure you've all seen one of these before. Your typical air source heat pump, one condenser outside tied to one indoor unit or evaporator or fan coil. All those words are interchangeable. A compressor is outside of that machine, on the outdoor machine. Here on the left, excuse me, not outside of the machine, it's on the outdoor machine. And then the evaporators on the inside. These are just one-to-one systems. Of course, you can do all your heating and cooling. And then the multi-split system, which is the system on the bottom right here, it's very similar to the mini split, except now we have multiple indoor units tied to one condenser unit with a dedicated pipes from the condenser unit to each indoor unit. So it provides a little bit better zoning. With this, the system is in either heating or cooling mode. So one indoor unit can't heat while the other cools. But we see these used quite a lot in residential applications, whether it's a single family home or also even multifamily projects, because it does still provide some level of zoning with separate thermostats per indoor unit with set points and schedules and all sorts of things like that. So moving on to VRF, or variable refrigerant flow. So this is the big brother version of the splits. VRF, it's extracting or ejecting heat from the outdoor air source machine. We also have water source machines as well. So these machines are a little bit larger than your usual mini splits. They can be modular, where you can tie multiple of them together into one refrigerant circuit, increasing the capacity of the system. The compressor lives in that outdoor unit, all inverter, variable speed compressors, very efficient machines. And then each indoor unit has their own expansion device and their own thermostat. And each indoor unit will modulate the amount of refrigerant depending on what each needs. So you vary the amount of refrigerant based on demand, hence the term variable refrigerant flow. So again, these could be water source or air source machines. Everything's essentially the same for both, but we'd either, of course, be rejecting or extracting heat from the outdoors or from a water loop. And then looking at the heat recovery version. Just on the next slide here. So VRF with heat recovery. So this is what VRF is most commonly known for. And this is where we introduce something with these branch boxes here shown, which is essentially an advanced version of the gearbox and reversing valve, which I mentioned, that decides that one fan coil will get heating while another fan coil will get cooling. So what happens if some fan coils are cooling and some are in heating, the system's able to exchange heat and save some energy that way instead of rejecting all of that heat outside. So you can then reuse it in the building, hence the term heat recovery. So again, this is what is typically what VRF is known for, and what we use most often for that simultaneous heating and cooling function, where one indoor unit can be in heating while another's in cooling. And there are centralized versions of these branch boxes here, or these advanced gearboxes, which have all sets of valves to decide to send either the for one unit to be in cooling or the other unit to be in heating. So all sorts of options with that, and that's what really is the go-to with VRF. Just to talk about moving on to the features and benefits. Just to talk about some of the general benefits of VRF. So usually the systems come with a central controller, usually a touchscreen central controller. It's sort of a pre-packaged building automation system where you can go and see and control all of the fan coils. Smaller buildings might just use that as their mini building automation system. You can even tie in and control other simple things in the building, like exhaust fans or fresh air machines. So if you have a smaller building, again, you can just use that. If you're a larger building, if you have a building automation system by one of the larger controls companies, you can also integrate the VRF systems using this central controller. So we use a protocol called BACnet to be able to talk the same language as these automation systems. There's also options for peak load shedding with some inputs if you want to tell the system to limit itself, either for running on generator power, or whether maybe you're trying to do some peak load shedding with the grid, and all sorts of options with that, which make pretty nice. And then flexible design and physical footprint. So one of the big things in our market, it's a big retrofit market. So how do you add air conditioning and how do you electrify that building and get rid of the boiler without pushing around big ductwork, air and big ductwork, or without running larger water lines? So here you're running small refrigerant lines. It's a mix of larger hard copper lines, around an inch and a half, which are the largest lines you'll really see. And you'll also see what we call line sets, or soft copper lines that are usually small, quarter inch, maybe 3/8, that are rolled up, similar to the image shown in the bottom right here. You can unroll and flexibly roll throughout the building. Then of course we have all sorts of inner unit options as well that we'll touch on in a few slides, which provides lots of flexibility. So a bit more about the benefits. I'm not going to talk too much about the high efficiency aspect. I already touched on it a little bit, and Jason will get into it a little bit more in a bit more detail. So comfort and flexibility operation. So one of the things to remember with VRF systems, that these are zoning systems that are meant to have multiple indoor units serving different zones, which is great for buildings that have various zones that might need heating, while others might need cooling. You might get an internal boardroom that might need cooling in the middle of winter, and then you'll have maybe exterior offices that would need heating. So VRF again is meant to zone your building, unlike a standard single zone rooftop with just one thermostat in your space. So there's lots of flexibility with that. Then the quiet operation, I didn't touch on this too much, but a water source heat pump will have a compressor in the unit, and that compressor is usually right locally in your space. might be in your condo behind a little panel, might be above your head in a ceiling, in an office building. So, and those compressors, of course, add to noise. So what happens with an air source heat pump is that we always put the compressors outside in the outdoor machine, or in one local water source VRF machine. So that has a big impact on noise, because the machine inside the building or in each zone ends up just being a fan and a coil. So you're essentially just moving air around. And usually these VRF fan coils are small little direct drive DC motors. So they're very well balanced, and they typically have very good sound characteristics. So before I pass it off to Jason, I'm just going to touch a little bit on refrigerants. So it is a very hot topic these days. Any refrigerant cycle, any refrigerant system, any piece of air conditioning essentially use refrigerants. So all these systems we're talking about, whether it's an air source heat pump, water source heat pump, ground source heat pump, those all use refrigerants. Now we had refrigerants. I think the first one was Freon back in the 30s. We eventually figured out in the 80s that those refrigerants contain chlorine, and those when they get up in the stratosphere get broken up by the sun rays. Then the chlorine starts to attack the ozone. So we had issues with refrigerants hurting our ozone layer. The Montreal Protocol came along, and we essentially phased out all CFCs and HCFCs. So all refrigerants with chlorine are all gone, including R22, which you might be familiar with. That is an HCFC. So as of January 1st, 2020, you can't even buy any R22 unless it's recycled. So we took care of the ozone depletion problem of refrigerants, and we moved on to using only or mainly HFCs or hydrofluorocarbons that do not have chlorine. So for example, R410A is what we currently use in all air source heat pumps and VRF. Again, it does not contribute to ozone depletion. The one, excuse me. The one thing is that once we start using these HFCs, is that they have more hydrogen atoms, and they tend to be a little bit more flammable. So what we do is combine them with some sort of flame suppressant in order to make them less flammable and safer to use. And that increases what we call the global warming potential, or GWP. So what happens is these refrigerants go up in the air. They do a similar thing that CO2 does when it goes up in the air in the stratosphere in terms of the warming effect. So, however, due to their characteristics, they're much more stable structures. The strengths of their bonds, they actually tend to have a much greater impact. The GWP of a refrigerant is how much more detrimental to the warming is it compared to the same amount of CO2. So an R410A is around 2,000 times worse. Of course, we don't want to put the refrigerants in the air. We're trying to keep them inside the machines, but eventually there could be leaks. If they're not recycled properly, they could end up in the atmosphere. So there are concerns out there around these refrigerants and how to reduce their global warming potential. There are currently no phase outs in the US at the federal level for R410A when it applies to air source heat pumps or VRF. There are things happening with the alternatives that are available out there called A2L refrigerants, and putting those in buildings and systems, which we're waiting on the building codes to accept. So there are things on their way, but right now there are no phase outs on refrigerants like R410A. There are, however, been some phase down rulings that came out recently from the EPA, or the Environmental Protection Agency, which we expect to open up a large market for recycled refrigerants in the future. So the final slide for me here, before I pass it off to Jason. Like I mentioned, if the refrigerants stay inside the system, then there's no big deal, and they get recycled, then that's okay. I think the recycled refrigerant market is where it's going to be a big part of the focus in the future. So we're going to look at using less harmful refrigerants to the environment, but we should also just work at keeping them inside the systems more. So the important thing in any air source heat pump that's going to run for 15, 20, 25 years is the efficiency at which it runs. So how much power it pulls. So that has the largest impact on what we call the life cycle climate performance of that machine. So for every kilowatt of electricity we pull, every kilowatt hour, we generate a certain amount of CO2 because the state of our current grid, which of course is improving. And there's ways of making on-site renewables as well. But today, your current grid will generate CO2. So over the lifetime of a unit, yes, we're trying to get better refrigerants, but we're also looking to make sure that that does not negatively affect the efficiency. So for every point of efficiency you lose on the system, that's 20 years of pulling more power. So we're looking into, again, lower GWP refrigerants. However, we're keeping our focus on the efficiency of these machines, especially with the current state of our grid. And then with refrigerants being such a big topic, there's a link here to a webinar that our DXS principal, JS, presented for NESI. It's an hour long, and it really goes top to bottom on refrigerants, and the GWP, and what's happening in the future for phase outs in North America. So with that, I think I'm going to pass it off to Jason. All
right, thanks, Adam. That was great. So we've talked a lot about VRF and heat pump technology. In VRF's name, it's variable refrigerant flow. Now I wanted to talk to you guys about variable speed compressors and what kind of impact that actually has on heat pumps as far as efficiency goes. So looking at this, we're going to compare two systems. Starting out, we're going to look at a traditional system or a conventional system. So that is going to be your constant speed on-off compressors, right? So you might find those in a rooftop unit, or maybe a central AC unit that you might have installed at your home or your parents' home. It's going to be constant speed on-off, right? So if we're looking at this animation, right, our set point temperature is at 75 degrees, right? Compressor is going to turn on because we need cooling, and we're going to start at 90 degrees and bring that way down to 75 degrees, actually a little bit past 75 degrees. Now, looking at the compressor side, we're going to ramp up right away, huge inrush of current, and then we're going to be at full bore around that 60 hertz in order to get that temperature to what we want. We want that 75 degrees to be comfortable, right? And as soon as we go past that, okay, we're going to shut off the compressor. So the compressor shuts off. What happens? The temperature rises in that space, right? Eventually getting to 77, maybe 78. Okay, the compressor needs to turn back on, and it's going to do that on-off cycling, right? So a couple things to note here and a couple takeaways to look at for this conventional system is, one is comfort, right? So VRF is a comfort heating and cooling solution. Traditional systems, have a little lack of comfort. As you can see that there is a large dead band between that set point temperature. We're 4 degrees on one side and we're 4 degrees on the other, kind of thing. So, looking at this, the occupant could notice a 4-degree temperature swing at certain times and might be a little uncomfortable in the space. It doesn't quite reach that set point, right? And then something else to think about is this on-off is, bringing a lot of current to these compressors, which actually does hurt the lifetime of a compressor and the durability altogether. But, more importantly, efficiency. These compressors are not efficient. This is not an efficient operation because we're not meeting set point and we're using, full bore on-off in order to get cooling capacity to reach that 75 degrees, right? So in comparison, we're going to look at a variable speed system or inverter-driven compressor technology, which is what are in heat pumps, right? So same kind of setup. We're going to have that set point at 75 degrees. We need cooling capacity, and we are going to turn on the compressor, right? And at that compressor, you can see it's not a steady line. It's actually a little jagged of line, which is basically showing that we do have a soft start in the compressor. So it's not going to get the current right away. It's going to slowly work into it. And then it's going to ramp up way past the 60 hertz you might see, on a traditional system. So the whole goal with this is to just work extra hard to get to that temperature we want to be. We want to be as comfortable as possible. That's where we're going to go, right? And where the magic happens is actually after the fact of when we reach set point. So as soon as we hit set point, the whole point of a heat pump system is to stay on. Typically with a conventional, it's just going to be on off. VRF, we want to stay it on. So, when you're installing a heat pump system in your home, you go, okay, it's getting hot in my house. Maybe I want to turn on my AC, and then you turn it off 2 hours later. That is not the function of a VRF system. As soon as you're getting away from set point, it's going to take a lot more energy and it's going to work a lot harder to get there. So you want to keep it on. And, you know, what's going to happen is, looking down at the compressor, we're going to ramp that compressor way down low, and we're going to only use the energy that's needed. So why does this really matter? This matters when you are designing an HVAC system and you're sizing it. And typically what you're going to be doing is sizing it for worst case scenario, right? So when you size a conventional system for worst case scenario, you're looking at, okay, you know, wintertime, it might be 0 to 5 degrees in the Boston area. And then, you know, the summertime, you might have a glass building or a glass section to your home. We're looking at 95 degrees there, right? So let's say we have a home and we need, you know, 4 tons, right, for a conventional system. All right, that's good. But what happens when, you know, it's 70 or 65 degrees outside? Yeah, we might need a little cooling capacity. So what's going to happen is that conventional piece of equipment is going to cycle on, off, right? And it's still going to probably overcool the space, and it's just not going to be comfortable. It's not efficient. Whereas, you know, you size a variable speed compressor or, you know, a heat pump system for peak load, what's going to happen is, on a mild day, you know, a spring day, if it is 70 degrees, it's going to ramp way down low to get exactly the right set point and use exactly the amount of energy, you know, it needs in order to cool off that space. And, you know, this is where the part load efficiency happens. And this is where we're going to start talking about, you know, the different types of efficiency and how they're comparable. So starting off the cooling side, almost all methods of cooling use a compressor and a refrigeration cycle. So Adam's talked about this a little bit, but, you know, large chillers, packaged rooftop units, you know, those PTACs, you know, that you see in hotel rooms or affordable housing, or maybe just your window shaker units that you put in your apartment because you don't have any cooling. All of that uses a compressor and some type of refrigeration cycle. So heat pumps are the same way, just like Adam mentioned. However, they're a little different in the sense of they do have a reversing valve, which is able to, you know, reverse the flow of refrigerant to either, you know, change where the heat sink is and the heat source is. And there's 2 types of, you know, cooling efficiency that are a little similar, but they do have their differences when we're talking about different pieces of equipment. So starting out, I'm sure a lot of you are familiar with this. You know, this has been around for a long time, but EER, which is energy efficiency ratio. And this is the cooling output BTUs divided by the electricity input watts per hour, right? And the important thing to take away from here is this measures at peak load. The efficiency is measured at peak load, right? So peak load, again, would be that 95-degree day or that 0 to 5 degree day in the wintertime. So in the Boston area, if you are looking at bin data, right, how much time is actually spent at those temperatures, it's not that much. Peak load at 95 degrees, yeah, even though we had those humid days, a couple of weekends ago at like 95 degrees, normally that's only about 1% of the time in Boston that you're actually going to have that. So if you think about it, you know, that's good for, you know, conventional equipment, but, you know, at the end of the day, it's not telling the full story of variable speed compressors. So you actually might, you know, look at 2 labels. You have a conventional piece of equipment sitting next to each other, and you have a heat pump sitting next to each other. You might look at the label and say, all right, the ERs are, you know, relatively the same number. And for those of you who maybe not be completely, you know, familiar with efficiencies, might go, okay, these are pretty much the same efficiencies. Why don't we just go with a cheaper option? It's going to work the same. And that is not the case, because peak load is actually the least efficient point in a system, right? So it's not telling that full story. And, you know, with a heat pump system with variable speed, you know, you might actually be at 50% load, right? And it doesn't work linearly at all, right? So you might be 50%, you're not going to have 50% power input. We're going to be ramping that compressor way down low to the point where you might only have 25 to 30% input. So it really doesn't tell a story, or EER really doesn't tell the full story. So that's why we have IER, which is Integrated Energy Efficiency Ratio. So what this does is actually takes a weighted average of the ER values at different temperatures. So what it's going to do is it's going to take different temperatures, it's going to take the different loading standpoints, and then it's also going to have time along associated with that, right? So you'd have, 100% loading, full demands, and we'd only be at that like 1 or 2% of the time, right? Then you have 75%, maybe at 60% of the time, and then 25% at 30% of the time, right? And you take all that data together, all those points together, and then you come up with a weighted average, an IER number that is giving you a full representative of how efficient that's going to be and how that's going to perform over the course of that year, right? So the big takeaway here is EER is perfect for, conventional equipment, on-off equipment. It's going to give you an accurate reading on, how it operates. EER for a variable speed is not going to tell you the full story, and you might want to look elsewhere, which is IER, which is going to give you that full story. So transferring over to the heating side of things, most commercial heat pumps, actually pretty much all commercial heat pumps, use COP as a efficiency metric. I know Adam's mentioned this a little bit, but that is the coefficient of performance, which is as simple as the energy in divided by the energy out, right? So Adam mentioned at lower temperatures, as it starts to drop, there is a D rate associated with these heat pumps, which is fine. We still have a higher COP than other things that I'm going to talk about, but we do have a D rate because it is a little bit harder to extract that heat out of low ambient air. But something that's nice to look at is, when we're looking at data, AHRI has manufacturers publish and test data for COP values at these two temperatures, at 47 degrees Fahrenheit and 17 degrees Fahrenheit. If you don't like those numbers, you're looking for something a little lower, what you're able to do is manufacturers have engineering manuals posted on their websites. So you can go to the engineering manual, and in there, they actually have a chart for both power input along with the different temperatures. So you can go through and actually pull certain COP numbers at specific temperatures if you're looking for just one temperature. And also if you want to know, okay, like let's see what that overall average in a year COP is, what you're able to do is take all that and then relate those numbers to bin data, and then you can take an average that way. So, 25 to 35 degrees, I'm spending, this many hours, and, 20 or 36 to, 46, whatever it is, I'm spending this much time. You can do that and get that average just so you kind of know how efficient your system is going to be operating, even though buildings operate differently and, things change throughout, an install and over the time of their life. And then we look at smaller units. So this is talking about our mini split units. So either a one-to-one connection or, a multi-split unit. But for heating, we're using HSPF, which is our heating seasonal performance factor. So basically, this is very similar to IER in the sense that it is looking at multiple data in the heating season, basically throughout the whole heating season. You're only going to be really using this for mini splits. Anything above 65,000 BTUs, this is not going to apply. You're going to be bumping up to COP, just like you would SEER. So efficiency is very important, but something to come to mind or bring to mind is efficiency is a lot different than cost effectiveness. Looking at this technology, the first one that's listed is a furnace and a boiler. We're all familiar with that. That's burning natural gas or burning something, right? So if we're looking at COP values, we might have an efficient boiler, condensing boiler that's 0.85 to 0.99 COP, right? So that's not quite 100% efficient. However, that is something that, could be a cheap alternative, right? That we think is a cheap alternative. And then we look at the electric resistance heat, which, people right off the bat say, oh, this is a bad solution. It's inefficient. It's going to cost a lot, right? And when we say inefficient, it's actually not inefficient. It is actually, perfectly efficient at 1 COP. It's going to put exactly, however many kilowatts it needs to convert directly or generate to that much heat. So it's not wasting any energy there. It's converting it, right? But when we start to talk about cost effectiveness, then we're starting to mention, okay, well, what's the cost of natural gas compared to electricity. Electricity is a lot more expensive. So that's kind of where it comes about, efficiency might be a little bit more, but if we're looking at gas prices compared to electricity, the furnace or boiler is going to be a lot more cheaper, right? And then we look at heat pump systems, which is a lot different than electric resistance heat. We are still using electricity. However, instead of generating that heat, using that power to generate heat, we're actually using the power to transfer the heat, as Adam's mentioned in his previous slides. So we're taking that air, that heat out of that ambient air and bringing it into a different space. And heat pump systems at that lower temperatures can be 2+, and maybe even mild temperatures that can be 3 or 4. So it's a lot more efficient that way, and it's just a solution to look at. All right, is this going to be more cost effective than burning natural gas? And the one thing I want to mention though is I'm sure a lot of you have heard that electrification is really starting to gain traction in the United States. A couple of years ago, Berkeley, California was the first city to ban new gas connections to new buildings, basically. And a lot of that had followed around California. And then New York City actually just recently published Local Law 97, which is the movement to not burn natural gas and basically to reduce greenhouse gas emissions by 80% by the year 2050, right? So there's some legislation behind that. If you don't comply at certain levels in certain years, there is going to be a penalty associated with that. And actually, other cities are starting to track on too. Seattle, Chicago, even Boston is actually coming out with a carbon performance standard for existing buildings within the next year. That's just trying to get pushed through now. It actually might be out by the end of this year, last time I checked. But basically, that's going to start in 2025, and that is going to be reducing greenhouse gas emissions by 100% by the year 2050. That's the goal. So just something to think into account. Yeah, maybe your gas boiler might be a little cost effective at this point in time, but eventually we are moving towards a more electric route, and we're going to have to be seeking better efficient technologies to meet those goals. So as I mentioned, when the temperature drops, it is a little harder for heat pumps to extract that heat out of the air. So the efficiency and capacity is lowered a little bit in colder weather. 20, 25 years ago, you might think to yourself, if you haven't been exposed to heat pumps that recently, you might think to yourself, heat pumps there's no chance we're installing them in New England. They can't produce heat whatsoever. And that's actually no longer the case. Now, any heat pump is pretty much able to extract heat out of the air below -10 degrees. All the split systems have kind of caught up. There are, low ambient heating capabilities for split systems, and also VRF technology. The larger ones can go past, -25 degrees. They can heat past -25 degrees. And yeah, that's cold, and yeah, that's probably not somewhere where I want to be living anytime soon. But as long as your refrigerant is colder than your ambient air, there is going to be some heat extraction with that, right? While maintaining a COP of around 2. So we're still, putting in 1 and getting 2 basically at that 0 degree temperature. So again, if you haven't worked on heat pumps in 10 years, you might think, okay, this can't heat past 20, 30 degrees, which actually was the case a while ago. And then you'd say, okay, well, now we're going to have to bring in backup heat, right? We need some kind of supplemental heat. Let's just bring in a backup boiler. When it drops below 20 or 30, we'll still have our heat pump system. That is really no longer the case. VRF has now been the sole source of heat in hundreds and hundreds of buildings. You do not need backup heat. However, if you do have an existing system, right, you could think about doing fuel optimization. Whereas, hey, it gets cold outside. I'm looking at my charts and my heat pump only has this COP and I'm paying this much for electricity, but I could just burn natural gas and it'd be a little bit cheaper, let's say, below 10 or below 0 degrees, whatever it is. And if you do have that existing system, that's fine, that works. Again, electrification is, kind of driving some of those factors, but right now that would be a perfect solution. The only thing to take away though is, VRF and new design does not need backup heat. It's more of a preference if needed. And then if we have low temperatures, we're designing, up in Maine or something like that, ground source heat pumps could be an option. As we mentioned, they are a fairly constant temperature. You might have, 40 degrees, and that is a lot more predictable than, in the wintertime, the air changing. So if you do want to look into ground source heat pumps, that's not a bad option. The only thing I would say is, initially there is a much higher cost for installation, and you do need to have an engineering team heavily involved in the process early on as you look at this type of approach. So out of a box, a VRF system or a heat pump system basically needs little to no maintenance, right? So we have inverter-driven compressors, we have high-efficiency DC fan motors, and all of these types of parts are designed to last the lifetime of equipment. You don't need to schedule any maintenance calls, replace your blowers, your fan motors, compressors. None of that's needed. It should all be intact and survive, 20, 25 years if need be, and potentially even longer than that. With that being said, don't ignore basic maintenance. That is still required, and it's very important, even though, we're talking about filters here, right? One thing is you need to check, clean, and replace those filters. We get stories sometimes. I'll just tell this one, my office tells this one quite a bit, but we got a service call maybe 6 years ago, and the building had been installed maybe 4 years prior. Get a call from the owner or whoever saying, hey, my cooling's not working. And, we're like, okay, we'll come check it out. We sent a service guy for the next day. And as the maintenance guy is getting ready for the contractor, he got a hold of, one of us, and one of my team members asked, hey, when was the last time you cleaned that filter? So the guy goes, I don't know. And he ended up going over there, taking out the filter, and immediately over the phone, you could just hear the airflow increase drastically. So right then and there, we're like, okay, that's where your cooling capacity is. So basically that filter wasn't cleaned for 4 or 5 years, which, for a, small fan motor or DC fan motor in a wall mounted unit, it was ductless, didn't have the external static pressure to actually push that air through that dirty filter. So, something to take away from that story is make sure when you're doing regular maintenance, preventive maintenance, check your filters every, 6 to 8 months just to see if they're clean and good to go, just so we don't reduce any operation that's set to do. Also, keep your outdoor coils free and clear of debris. This is also very important. We do need that air to flow freely through the coils to produce the right amount of nominal capacity, that's designed for. A lot of the time, what you can see is, sticks. You can see acorns, like sap, Dunkin' Donuts wrappers, cups, really anything. We've pretty much seen it all. But just make sure that's free and clear. If you do need to wash the coils, do not use any chemicals whatsoever. You're going to be using just water and a rag. We'll get the job done. So make sure that's cleared. And then lastly, what's pretty important is maintain condensate removal for these systems. So if we're looking at a indoor unit, kind of go up there when you're maybe replacing the filters, check the condensate, see if the pan is blocked off, see if the pipes are blocked off, anything like that. See if the pump is operation and running. That way you don't get any clogs, anything like that. If the pump fails and maybe you ruin some ceiling tiles or furniture down below, you want to stay away from that. If you can do gravity drain, gravity always wins. I know a lot of the time that doesn't really work, because typically you're going to need some kind of lift through your plenum. But just something to think about there. And then lastly, use manufacturing service tools. Every manufacturer has a service tool that's able to record system data. So a lot of the time, you'll have a guy go out with the service tool for startup. And basically what they're able to do is take an hour to an hour and a half run time of data And what that shows you is all the working, pressures, temperatures, and to see exactly how that system is operating and see if it's operating correctly. So, right after install, we're making sure that, this is going to work, there's no issues, and you kind of leave the site then. But what's also nice is if you have that same tool and you have that recorded data from day one, let's say you go, 5 years later, they might be having an issue or whatever the deal is, the service guy can bring that first reported, system data and plug in the service tool and get 5 years later, and then you can kind of compare it to see, if there's anything changed or if it's running just how it was on day one. All right, so it's been about an hour now. Let's go ahead and take a 10-minute break. Why don't we all come back at 2:15, and we'll try to answer some questions, and then if not, we can get to it at the end of this presentation. But let's come back around 2:15-ish, and we'll go ahead and get started on outdoor units, indoor units, and a small ventilation overview. All right, it is 2:15 now. I'm going to assume that everyone's back at their desks and ready to tune in again. So this section is just going to be heat pump equipment options. We're going to briefly discuss outdoor units. I know we've done that a little bit. And then we're going to kind of go through each individual indoor unit that's available as far as, flexibility and what fits, your needs or building owner's needs. And then we'll just touch upon ventilation overview as well. Give a little background and, what the approach would be for a VRF system. So looking at this, there's really multiple different types of outdoor units that you can kind of pick and choose from to best fit your application. So looking on the left-hand side, this is typically what you're going to be looking at if you're talking a VRF system, right? So this would be your Airsource heat pumps. Then over on the right side, we're looking at, mini splits. In this case, this was actually on a commercial application, but, a mini split would look something like that, mounted on a wall or mounted on the grid stand. So looking on the left-hand side, the bottom picture of the VRF equipment, this is actually 40 tons of equipment. So this would be more of a central approach to a building, just running refrigerant lines, maybe in the center of the building, and then kind of sporadically putting them out onto different sections, right? So this is 40 tons. This is a good install. As you can see, they're up on stands, which Adam has mentioned. And the reason for that is there's two reasons. One is because condensate does come from the bottom of these condensers, right? So if they're placed on grade, what happens at certain temperatures? Adam mentioned, that 25 to 40 degree range. There's potential that condensate can, if it's not drained properly, can start forming ice and start building up to the point where it can get in the coils and crack the coils. And, with a cracked coil, everyone's having a bad day. That's going to be a lot of phone calls. So make sure you get these units up on stands. Typically, we recommend, 6 inches above the highest snowfall. So around the Boston area, we recommend 18 inches. Maybe if you start going to the Portland, Maine direction, you might be looking at 24-inch snow stands. As you notice that these stands are also opened up, when you're locating these, you don't want the snow to drift and pile up on these coils to block the airflow that way. So we have open stands so the snow can freely move through. And also on the other two pictures, you see, these hail guards, these robotic looking things, and, top picture, snow hoods. Maybe they don't look the best, but, these do provide insurance on your equipment, right? These 40 tons of equipment is rather expensive. It's a premium, right? What's a couple $1,000 more for some sheet metal to protect those coils and make sure that they are surviving, that lifetime that they're set out to do. So looking at that, we're going to go over to the right-hand side, which is our mini splits, right? Where did mini splits typically start? It probably started in the United States around like 30 years ago. And with that, you'd probably add like an addition to your house. You didn't want to extend your boiler route, or you didn't want to extend your central AC. So you ended up saying, all right, I'll buy a 1 ton or a ton and a half, unit here, and I'll put that in the addition of my house, right? Now they've kind of just taken off. They do have the capability of low ambient heating. And basically you can also use them as, multi-splits. You can have one of these guys. They're going to be a little bit taller, but you could have like 3 or 4 zones to get, your living room, your kitchen, and maybe your 2 bedrooms. So these have really taken off. These are for more single family home applications. However, they've been becoming increasingly more popular in the commercial world. This screenshot is actually a multifamily residence in Springfield, Massachusetts. And, these are actually used as, 1 unit per apartment. So you have up to maybe 2 tons on these smaller guys, and that's feeding 1 apartment. So you have 1, energy bill, and the tenant is paying for that 1, heat pump system, right? And you have, in this picture, 12 of them feeding 12 different apartments. So now I'm going to go through indoor units. There's about 11 different types of indoor units. Honestly, I could probably talk to you guys about this all day. So I'm basically going to choose a couple applications where they're seen a lot of the time, and just list off a couple of facts that might be good for you guys to hear. So starting off, we're starting off with a wall-mounted unit. Just to give you a little background, these are the most popular units worldwide. Over in Japan for HVAC, they're probably using about 95% heat pumps over there. That's where VRF was basically first invented. So all of those heat pump systems have a wall-mounted unit basically on every single one. And then if you look at Europe, Southern Europe, maybe we're at 75% heat pumps for these wall-mounted units. So they're really everywhere. It's the popular choice. And America is starting to gain a little more traction towards actually using these guys. I'm sorry if there's any architects on this call and they're pulling out their hair, but there's a reason why we're installing these now. Or at least they're becoming a little bit more popular. And the reason for that is they are the most efficient, right? They have a small DC fan motor. That's where a lot of the efficiency comes from. And they don't have to push air through, large ductwork at all. And then another thing is they're actually the most quiet. A lot of the times you'll have these guys and they'll be running at anywhere from 27 to, 32 decibels. So a lot of the time, like you're in office space, like showing, not even going to be able to notice that it's on. Sometimes that's a good thing. Sometimes that's a bad thing. But yeah, they're the most quiet. And then also they're the least expensive. You could probably get 2 or 3 of these for maybe the price of a ducted unit at times. So, those 3 things kind of combat to why these are becoming a little bit more popular in the United States. And honestly, you put it up on the wall and you forget about it after a while. So next up is our ceiling suspended unit. We typically call this the classroom unit. You can basically throw it up in a corner and again, forget about it. But what's nice about these is, for a school-like setting, right? A lot of the time you have like hot water piping going throughout the whole building. And there's not a whole lot of ceiling space where you could potentially put a ducted unit. So the next best thing would be to suspend the unit, right? And then it has a large throw of air. It's one of the largest. So it basically, cools off the whole classroom and has tons of capacity and potential to do that. It's also nice it's out of the way. Kids don't put their backpacks on it or, draw on it or throw crayons or, it's up out of the way. It's there, but, you forget about it. We also use these once in a while in kitchen settings. You need a large cooling capacity, almost use it for like spot cooling almost. They don't really care what it looks like as long as it, keeps them cool, but if they're standing next to a fryolator or something of that nature. So that's also a good application when we would use a ceiling suspended unit. So another indoor unit is our floor standing. There's really 2 types here. There's your exposed, and then there is your concealed as well. So this picture is showing the exposed, right by the window. What's nice about these is you can place these fan coils exactly where the bulk of your load is going to come. For this example, this looks like a older historic building, maybe a loft space. Where a lot of that solar veins coming from these windows. So one thing would be to just get that cooling capacity right there, and you'd be all set. 2 refrigerant piping comes directly to this unit. So not much room that's taking. There's not a whole lot of room that it's taking up. Then we go to our concealed floor standing units. I forgot to mention, but the returns down at the bottom, and then you have your supplier coming up the top. I call these the church models. And the reason for that is we don't really like to touch, what's already there, what's already been built in the church. However, a lot of the time you want to replace, your heating source that's, way over the lifetime. So what you're able to do is rip those out and end up adding in these concealed units, basically, take a little window out, and then you can go back, do the same millwork, and it almost looks like, you haven't even touched it. It looks the same. However, you are getting now cooling and heating out of this unit. And then we go to maybe the more popular units in the United States, and that's because we really can't see them. We don't like to look at, what's feeding us cooling and heating a lot of the time. So we like a better aesthetic. But yeah, the first option is medium static ducted unit. This has a pretty good throw overall. It has up to 0.8 inches of static pressure, so it can do a long route of ductwork there. And it stands about 11 to 12 inches tall. So that would be perfect for, an office space scenario. And then you look at your low profile ducted unit. This is probably like 7 to 9 inches tall. And what's great about this is showing in the picture that you have a soffit. Basically the ceilings drop down low, and one of those low profile ducted units is sitting in this hotel room. Kind of see that all the time, and barely any duct work, but it fits there perfectly and does provide heating and cooling to this hotel. So something like a medium static would be probably a little too tall, but low profile has the perfect fit. And that static pressure is only about 0.3 inches there. Then there's an option for high static ducted units. These are typically used for, hey, I have a lot of capacity that, I need to bring in. I need a lot of CFM. Why don't we take one of these ducted units? Perfect application would be, a large lobby space, a pretty open room, or maybe even an auditorium. I've used that in a couple scenarios, but this has a little bit more static pressure than the medium static. It's up to 1 inch. A little bit larger, but this does get the job done if you want more capacity, anywhere from 6 to 8 tons at the maximum end. And then this is something that's very similar to an air handler that we might be used to. This is kind of the American version of this type of fan coil. But this is a vertical ducted unit, or also known as a multi-positional ducted unit. And what's nice about these is they have 3 configurations. You have an upflow, you have a downflow, and then also you can put it on the side and have a horizontal flow. So what these are great for is, high rises or like multifamily buildings where you can take out that existing water source heat pump that's end of life and shove that right into the wall right there. And then all you need is about 18 inches in the front for clearance, and then you're good to go. So choose your orientation, good to go. And then we get into our cassette category. We do have a one-way ceiling cassette. These aren't too common, but the whole point of our design intent behind these was to look like a linear diffuser, which they do. So you have one-way flow here, and then you have your return grills out the back. And really the best application for these are, office spaces, but mainly open office spaces where, you have a large glass window going all the way down. You have a lot of solar gain from that. Let's flush that out with cold air and neutralize that solar gain. So that's typically what they're used for. Something like this picture depicts it perfectly. And then there's options. These are very common as well. You've probably seen these in hotels, schools, office spaces. But these are our 4-way cassettes. There's a large 4-way cassette that's a 3x3 model. And then there's also a 2x2, which is the smaller ceiling cassette. So perfect application right here would be a conference room, right? Nice thing about the larger cassettes, they do have more capacity. And also you have your, return in the middle with a filter, right? But what's nice is you can actually, on the larger ones, you can open that up and actually service it from the bottom. You do not need an access door. And then you have your supply air coming out on all 4 vanes, and these can be adjusted through controls. And then the small cassette, same kind of thing, setup, except you do need to have an access panel, which shouldn't be a problem for a drop ceiling like this, but you do need an access panel for these smaller cassettes. All right, so something that was not on those slides and that I did not mention was a question I get a lot of the time, which is which ones of these fan coil units can accept fresh air? So that's a great question. And basically the floor mounted units and the wall mounted units do not really have a way to accept fresh air. You can't bring it to the back of the unit at all. So typically what you'd be doing is dumping it directly into space. You don't want to be dumping in raw air to the space, right? You probably want room neutral air to bring that fresh air into the room to meet the requirements code. All the other units, the ducted units, you can easily bring air to the back of those units, have a mixed air cowl, good to go, just get the right temperature. And then your ceiling suspended, as well as all your cassettes, they do have a 4-inch round knockout, where you are able to bring a small amount of fresh air, anywhere from 0 to 50 to 60 degrees, no more than that, because if we bring more than that through a 4-inch duct, it's going to sound like a jet going over your head. But you are able to bring some fresh air, and typically with those cassettes, you're feeding a smaller room anyways. But yeah, if you are dealing with wall-mounted units, you're going to have to be dumping the air directly into the space. And transitioning into ventilation, kind of to state the obvious here, all buildings require fresh air ventilation of some form, right? So, many years ago, 10, 15 years ago, we still kind of get away with it, but 10, 15 years ago, we would actually depend on, windows and passive air leakage for ventilation, which I can tell you right now is very, very inefficient, right? It's going to often waste energy. You're just bringing in raw air and you're bringing in, 20 degrees, right? What does that mean? That means your HVAC system, your heat pump system has to be, grossly oversized, or not even oversized. It just have to be completely upsized in order to, meet that temperature, because you're constantly going to be fighting with the windows if you're leaving your heat pumps on, or even the passive air leakage that you kind of left there. And also something to note is, it doesn't ensure air quality whatsoever. If you're opening your window, a lot of particulates such as pollen can get in, and that's not great quality of air, especially for people who have allergies and other particulates as well. So very inefficient. Wouldn't recommend that. And a lot of the codes, the newer codes in Massachusetts, have kind of really pushed away from that. That's really no longer a thing. What you really need is some kind of ventilation system in order to introduce that fresh air into the building. And I have this last bullet point. I know we've gone through a pretty tough time with COVID-19 over the past year and a half. And this conversation's come up a ton, what can we do to minimize virus transmission? So I just want to give you a couple bullet points, but basically, as heat pump manufacturers, we are able to integrate certain accessories to help out with virus transmission. So the first bullet point is filtration. We can't go that high in filtration. We can't get up into the HEPAs really, HEPA 18, 19. However, we are able to provide, MERV 13 filters on all of our ducted units, as well as, if you add an accessory to our cassettes, you can either get a 10 or 13 MERV filter. If you're not really comfortable with that, you want more than filtration, then you can start looking at these other two options, which, the more popular one I'd say is UV lights. This is pretty effective overall. So if you did want to install UV lights in your ductwork, maybe your return ductwork, right before you hit that, mixed air, you can do that, or you could do it more in a centralized location. Maybe if you have a large DOAS system dealing with all your ventilation air, maybe you put, UV lights in that DOAS or, in that return duct before it goes back out, or before it hits the wheel. And then there's also bipolar ionization. This is a little bit new to me, but basically what this is it sends ions into the space, and the electrons actually, kind of merge with particulates, bacteria, viruses, and they kind of form bonds. And these bonds actually help with virus transmission because they, form together, making the molecule of the particulate larger. Typically, a COVID molecule or, a virus molecule could be 0.02 microns, which is very, very small. But, ions form with electrons, they kind of come together. And basically what happens is those particulates either drop to the ground, whereas, typically with smaller particulates, they could be up in the air for, 4 or 5 hours. But also it helps with, forming them, making them larger to the point where they'll catch easier infiltration systems. So, that is also a method. As heat pump manufacturers, we are able to, integrate these accessories and, make it fit your system as best as possible. So a little bit more on ventilation. So most heat pumps provide cooling and heating, right? So, they're not really focused on fresh air too much, and, typically you'd want to have some kind of dehumidification because we're controlling to, sensible temperature, and we're not controlling to latent, which is your moisture in the air. So you want some kind of, ventilation system that can deal with that. So your first option, which, I don't typically recommend, is you can bring raw outside air and, try to dump it into a space. First off, that's not going to be comfortable. And, that's going to also increase your, heat pumps, your HVAC equipment by a ton. You're adding a lot of first costs on because you don't have something to really treat that air. So the second option, probably the first option, we'll forget about what I just mentioned there, is using an ERV with a static core. So if you want some kind of energy transfer, you don't want to waste the heat that you put in to a building, what you're able to do is, bring in your outside air and mix it with your return air. So you could have 70 degrees as your return air. Let's just say worst case scenario, it's 0 degrees in Boston. So we're mixing that together and you might get 35 to 40 degrees, right? And maybe if you did like a little mixed air and brought that to the back of the fan coils, that would work. You might need to upsize your fan coils a little bit, your indoor units, but that could be a possibility if you're dealing with that. That's also worst case scenarios. You can get better, if we're at outside temperature of 20 degrees, you might be getting 50, 55. So just something to think about there. But also what you can do is use a DOAS system. So you can have a rooftop unit that has a wheel, transfer energy there. So if we're at 0 degrees outside, that wheel brings it up to 30, 40 degrees. And then you have some kind of mechanical, system that heat and cools the space. So if we're in heating mode, we could have, natural gas burning, or we could have, electric coil of some sort, or even you can connect heat pump systems to get your heating capacity that way to bring, that 40 degrees off the wheel up to room neutral air at 70, 75 degrees. And then the other way around, if you are worried about dehumidification, I know a lot of people are, it's very humid in the New England area. As we could see, 2 weekends ago, it was pretty miserable overall. But if you're worried about dehumidification, let's say, it's a 90-degree day, 70%, 75% humidity, what you can do is off the wheel, we can bring that temperature all the way down to 55 degrees, which basically takes that moisture completely out of the air. And then we're able to use a reheat coil, a DX coil, to heat that back up to room neutral air. So that is also a method, but basically, how would you bring that air into the space? Couple different approaches you could do. On a DOAS system, you could have a central DOAS system where, you just have one long duct chase and it's just sporadically putting it out to different areas of the building. Some people like to do, multiple rooftop units or multiple ERVs, let's say, on a certain wing of a building, or a floor by floor basis. And then, sometimes if you're in a multifamily situation, you might have, your AC and heating in an apartment, but you also have a dedicated ERV for ventilation air. So that's also an option if that makes sense for the application you have. But whatever you choose, make sure, you are providing some sort of ventilation in your building. It's required. And really where you're going to bring it as far as are you going to dump it into an unoccupied space, or are you going to bring it to the back of these fan coil units that accept ventilation air and go from there. All right, I'm going to pass the torch off to Adam, and then I will be continuing later on.
Awesome. So getting into applying these heat pump systems for different buildings. So here we're talking about the difference between air source heat pump and water source heat pump. And of course, we already introduced the technologies for these earlier on between the two. So now we often talk about higher efficiency buildings and going towards net zero buildings and all electric buildings without any gas. So really in those cases, we're comparing an air source heat pump with a geothermal water source heat pump, also known as a ground source heat pump. So the ground source heat pumps are the only way to electrify water source heat pumps, or almost the only way to make it all electric and not need a boiler, is to have that water go through the ground or through a body of water, like a lake or something like that. Now talking about capital cost differences. So when it comes to trying to go all electric, which is what this slide refers to. So one of the first things to look at is there any existing infrastructure if it's a retrofit building? So is there an existing water source heat pump loop where the pipes can be reused and then possibly converted to geothermal? In those cases, it makes a lot of sense to look at water source and ground source heat pumps with some of that infrastructure cost right there to be reused. If there is no infrastructure, just bricks and mortar, if it's a completely new building, then a lot of people looking to go all electric will often try to compare air source versus ground source. And generally, the air source heat pump is going to be your lower capital cost up front, as I already mentioned earlier. There's much less infrastructure. Again, the condensers outdoors, which I already touched on, indoor units in the building, whereas the ground source heat pump needs that entire hydronic infrastructure, all the water and loops, which tend to be higher capital cost. There are, I think there's companies out there that actually fund and finance that portion in the ground source heat pump world as well. Now, your ground source water source heat pumps can generally be lower operating cost than your air source heat pumps. Again, it depends on what you're using for water source heat pumps. Like if it's simple on-off compressors or variable speed compressors for the heat pumps, then also on the hydronic pumping side, if it's variable speed pumping or constant speed pumping. So a couple things, again, to consider and look at what you're using. And also don't forget that there's also water source VRF that you can be used and kind of combine the two technologies there. So in terms of retrofit applications, just on the next slide here, a forced air system, or what type of existing distribution? That's a question. A forced air system, which is usually a machine that will move air, whether that's a vertical air handler, a horizontal air handler, and you're looking to go with heat pumps, then you could look at the water to air heat pumps. Those are your typical water source heat pumps, like I already spoke about earlier. Those are still forced air systems. At some point in the ceiling or in your closet, you get a machine that moves air and heats and cools that air as well. The air-to-air systems, which are the air source heat pumps, which I spoke about, also forced air systems. Obviously, with those, you can get into the ductless world of wall mounts and cassettes that Jason just spoke about. So it's still moving air around, but it's an air source heat pump. On the hydronic side, which essentially means you're moving water around the building, whether it's through radiators or even can be put through fan coils. Then we get into the other types of systems we talked about earlier, the water-to-water systems, which is usually a heat pump chiller that will connect to a geothermal loop, and then it will generate hot and cold water for the building. So some large net zero schools are using this technology, which is pretty efficient. And an air-to-water system, essentially, which I've already talked about, is an air source heat pump that will generate hot and cold water directly from the air for the building. So it does depend on how you're planning to distribute your heating and cooling throughout the building, whether you do want the forced air system, whether you do want those radiators, because it might be maybe an older retrofit building with a lot of glass heat. So sometimes, no matter what, you might be looking to have the hot water run near the perimeter of the building, which happens on some jobs. So those are some things to look at. So it is pretty application specific. So from there, I think I'm passing it back to Jason already. Okay, sorry, I think maybe another couple slides.
Oh, sorry, Adam. I didn't take myself off mute there.
I was like, I'll keep going.
Yeah,
all good.
Yeah. So sorry about that. So a couple questions that we need to ask ourselves have to do with zoning. Do we need simultaneous heating and cooling in certain zones? Going back to an application, let's say, a box store, for example, We could do a Walmart, Home Depot, whatever it is, right? That needs a lot of CFM, and it's really one zone or couple little zones here and there that just have a high CFM, right? So, that might not be the best application for VRF and zoning, right? If you're dealing with a larger building, maybe 2,500 to 100,000 square foot building, maybe it's an office space, that would be a little bit more useful for when applying VRF technology, because you might have a conference room, right, with 15, 20 people in it, right? It's maybe close to the dead of winter, right? And you might need some heating out of that, or sorry, you might need some cooling out of that, whereas all the exterior office spaces need heating. So just something to think about. Do you need simultaneous heating and cooling, or do you have an application where maybe you have classrooms, right? And maybe you're at a more of a lower budget. Hey, these students don't really need cooling; they just kind of need heating at this point. We can do heating or cooling at one time. Why don't we just keep it a heat pump system, and we'll do a schedule based on the seasons, basically. So shoulder season hits. If April 1st hits, we're going to go to cooling mode, and then October 1st hits, we're going to heating mode, basically. So not everything needs simultaneous heating and cooling, but most applications with a lot of zoning do. And then also, if you're looking at a smaller office fit out, right, you maybe only need 5 tons there of cooling capacity. Maybe just have an open office space with like 1 or 2 offices. That might be a good opportunity to just provide mini splits. Don't get a huge VRF system that's 3-phase. Maybe just use a single phase condenser there and supply the load that way. And then when we're talking about zoning, this relates to multifamily housing. Is the owner going to build the tenants, or is the owner planning on taking the electricity that's used or utilities that are used and adding it to the rent? And this is a very important question to kind of figure out, all right, which system is going to work best, right? So if the owner answers, hey, I want the tenants to pay for electricity, then maybe the best option would be to look at split systems, right? Because you mentioned dedicate 1 split system per apartment. They have their own meter, and then they're good to go. They'll be billed that way, right? There is other solutions for VRF systems. Let's say you did install a VRF system and it's feeding 20 apartments. There is energy allocation out there, which basically, meters and takes into consideration how many kilowatts are being used at each fan coil unit. However, right now in Massachusetts, it's a little foggy subject. Legislation is still working on it to make it approved. Places in New York City and Rhode Island use energy allocation all the time for tenant billing, as they're using VRF systems. But anyways, if an owner did say, hey, look, I'll put it in the rent, then you kind of have a free for all. If you want to use a VRF system, you can. But something to go, backpack off that is a lot of the time, developers will have apartments, they'll make an apartment building, and then they decide to, convert those into condos, start selling them off, right? So in the situation where you're dealing with, a VRF system that's feeding 20 apartments, we're starting to talk about ownership here, right? So if I buy an apartment and, my neighbor buys an a condo right next door, what happens in 15, 20 years when that VRF system that's feeding 20 apartments goes down? Who's going to be paying for, the service costs and all that? Maybe that could be a contract thing, but, that might get a little annoying. So maybe, if you do you're converting to, condos later on, maybe just dedicate a mini split to that condo. And when the person or, couple buys that place, then, they'll be buying the heating and cooling along with that. So it's their responsibility if anything were to happen later on. So just a couple zoning things and, things to think about when you are working with multifamily. And also that doesn't have to be multifamily. You could do the same thing with, office condos, right? You have a tall or high-rise building, and instead of putting, a large VRF system on multi, office sections, maybe you just put 1 on each one, just so, later on, if they are buying, that office space, then it's going to be theirs and they're going to own that HVAC. And then this is very important as well. Take a note of this one, but before you're even designing a heat pump system, you need to look at the building envelope, because, you know, a lot of the time you can just take a low-hanging fruit and, you know, fix the building envelope to save you a lot on something else. You might put an initial investment down of, all right, let's improve the insulation, you know, let's improve these windows. That is going to correlate directly to, you know, your heating and cooling and what you're going to be doing. It's actually going to save you upfront costs, because, you know, if your building is more tight, that means you're not going to have as much solar gain. That means you're not going to have a lot of heat loss. So that means basically your overall tonnage of your heat pump system is going to be lowered at first cost. You're not going to need as much. So that's just something to consider. You know, the way electrification is going, and, you know, the meeting I was on with, you know, Boston coming up with their electrification plan, it was kind of in steps. And some of the steps, or recommended steps, were look at your envelope first, you know, fix that, and then start to look at your cooking and domestic hot water, what's feeding that. And then your ventilation system, is that using natural gas? And then lastly, you know, your heat pump systems in general. Okay, you know, or your electric systems, what are you using for heating or cooling? So those steps are going to kind of go in order, but it's really important when you're sizing, you know, your heat pump systems, to make sure that, you know, you're not doing any last minute changes to your building envelope, because that does change and that does affect the system. And you want your heat pump system to be sized correctly, or all those, you know, all those efficiency terms that we're talking about, you know, you might be chasing a little bit more, you might not be getting. So this is getting into, you know, asking the right questions to find the right people to work on a project, right? There's different ways you can go about a project, but let's say you have a project, you know, maybe you want to go the GC route, get a GC involved, and, you know, do have a design build. So they're completely designing it, they're going in, they're contracting out the work, you know, they're installing it, and then they're doing, you know, start all the way through. Or maybe you want to go hire a mechanical engineer who does a complete design for you and then bids it out to any mechanical contractor or general contractor that's on the job. But whatever you do, you should be asking the right questions, because these questions are important and you got to understand why. So first is ask auditors if they will consider heat pumps as well as upgrades of existing fossil fuel equipment. So if you do have existing fossil fuel equipment, that's fine. You know, maybe it's not end of life, you can keep it. But just make sure you ask the auditor, you know, is by adding heat pump systems, am I going to get more cost savings? Maybe take advantage of rebate incentive programs. You know, is this going to be better off? Maybe you could even start with, you know, fuel optimization. Hey, you know, it makes sense to add heat pumps on because you're getting such a high COP at, you know, 40, 50 degrees, and maybe just use your fuel for, you know, 20 or below. And then as soon as that fossil fuel equipment that might be existing, you know, is ready to leave, it's kind of done, it's kind of crapping out, then you can use your heat pump as the full source of heat there. So, you know, just something to think about. And maybe even heat pumps are, you know, cheaper than going back and completely refurbishing your existing fossil fuel equipment. So next question is, why is the proposed technology a good fit for my building? We've kind of mentioned by now, it's not all one size fits all. You know, everything's different. You know, the buildings are different, they operate differently, and technologies are different. So make sure when you are running, you know, this application by someone, you know, you ask why or why not is a heat pump a good fit for my building, and just make sure you understand why that is. Has the proposed equipment been properly sized for my building? This is something that I can't express enough. You know, many years ago, you might have had a contractor that would just do a quick walkthrough, you know, stand across the street, look at the building, go, yeah, it's about, you know, 5,000 square feet. Let's use this many BTUs. That's no longer the case. We do not want to be oversizing our equipment whatsoever, because again, if you're oversizing your equipment, that means you're not getting the efficiency. That means you're going to do, you know, more of a short cycling process, and it's just not gonna work out. So make sure, you know, when you're going about a new project, to get your loads, design loads in, and, you know, make sure the proper calculations are done to size your equipment correctly. Another thing is, how do installation operating costs compare to alternatives? you know, right off the bat, I see this a lot of times, you know, a GC will have to put together a quote or basically budget pricing for, you know, VRF technology. A lot of the time, you know, some GCs are completely new to it, but honestly, they're catching on. But basically right off the bat, you'll see, okay, if we're doing, you know, apples to oranges here, the installation cost of a VRF looks a lot higher than maybe some of the other equipment. Then what you really need to be doing is looking at apples and apples, which is, you know, installation, operating costs, and maintenance costs as well. And you just got to go through and really compare those. And you might find yourself that, you know, through the operation or lifetime of the equipment, that heat pumps may be better option for your building because you're going to get a high ROI. So, you know, always compare alternatives before, you know, you jump into anything there. And then the most important one on this list is, has a designer, contractor, installer, whoever you're working with, completed training. Training is very important for, you know, heat pump technology. You know, everyone's got to know what they're doing. They have to be up to date. And the reason for that is, you know, this industry is constantly changing, and every year or two, there's new technology that's coming out. And, you know, if you haven't taken a course in a little while, you're not going to understand, you're not going to even know that that technology is out there. So, you know, if a contractor has not regularly gone to service training, that might be a problem, you know, in the field where they need to do an install, or, you know, they have a service call where they might not be too familiar with that equipment. And not to mention, whoever you're working with, if they haven't, you know, been to a class in 10 years, you know, they might tell you, or maybe 15 years, they might tell you, oh, no, I don't think heat pumps can really produce heat in this environment. And we know that's not the case. So, like, you know, you got to make sure you're getting the right recommendations from the right people. And, you know, training is a huge portion of that. So just something to note. And then also, that what kind of ties into it is, when was the contractor's last installation of similar scope, right? You have contractor A, that you have a large building, you have contractor A that's done a ton of 100,000 square foot heat pump jobs, right? And you have contractor, you know, B that's done a couple heat pump split systems there, couple more split systems there for maybe low ambient cooling application. It's probably best that, you know, you make sure the contractor you choose has a similar scope or has a similar background. There are contractors out there that just do larger jobs. So those are probably the people you want to talk to when you have that caliber of a job. So make sure you know that the experience of the contractor as well. And some resources that are really nice. All the manufacturers have a website, and they have a list of contractors who completed the training. So, you know, you can do a couple of things with this. What's nice, maybe you have a relationship with a contractor you've worked on a couple of projects with, right? And maybe the contractor really hasn't worked with that manufacturer, or whatever the deal is. Maybe they just aren't up to date. You can kind of go on that website and check where they are, just kind of, you know, cross, hey, is this the person for me? Even though I have a good relationship, is this person going to get the job done? Am I going to be satisfied with this project? On the other side, hey, you know, this is my first project. I'm just starting with heat pump technology. You know, I need to find a couple of contractors in my area. You can go to a contractor portal on this website and, you know, actually find certain contracts in your area and see how much training they've completed and if they're up to date. Which, you know, if they're on that website, they should be up to date. So scheduling, and also there's scheduling of upcoming training. If you or you know someone that's interested in attending this training, you know, there is schedules. If you're a contractor and want to, you know, attend an installation and service course, there's trainings for, you know, certain applications for engineers. There's, you know, sales courses. There's pretty much anything you can think of. And, you know, we're cycling people constantly, you know, through these training centers because this is very important to us. And, you know, this is directly correlates to having a successful working system installed in the first place. So if you're looking for training, you can contact, you know, either Adam or I, or, you know, look on the website. And then Mass CEC has a designer installer list as well. They actually did have a great credible rebate program not too long ago. I'm not sure if the funding is still there, But one of the requirements is the designer and the installer needed to be up to date on their courses. They need to show that as proof. So, this is a good running list of all these, contractors and designers that were up to date in those courses and were able to, push this rebate through. So that's another great spot to look. And also, if you're looking for, incentive or grant programs, there's a bunch of these. You have APS, which is Alternative Portfolio Standard. You can go to this website, see if you apply for, any energy alternative credits there. Mass Save is always great. They have constantly updating, their rebate programs, or you can just contact your utility representative that's in your area. They're definitely up to date, and they're good people to talk to. And then municipal utilities, if you're served by a municipal utility, contact them, or you can reach out to, Joe Coles at Massachusetts Municipal Wholesale Electrical Company. That's his email right there. So all great resources if you are looking for, that incentive or grant programs. They're out there, you just got to find them. All right, looks like we're doing pretty good on time. So why don't we take another 10-minute break, and then we will wrap up with our 2 case studies. Shouldn't take that long, and then we'll kind of go into, question and answer any questions that we might have not already in the chat already. So let's come back at 3:12. Kind of a weird number, but we'll be back at 3:12 and start talking again. All right, it is 3:12 now. Let's go ahead and continue. So Adam and I have two case studies that we're just going to quickly go through and give you a couple examples on, what an application was and, how we went about it. So today I wanted to talk to you guys about Clark University Alumni Center. This was completed in 2016. This was a new construction building located in Worcester, Massachusetts. So this building was a pretty square rectangular building and about 35,000 square feet. Main objective was to kind of go net zero or net zero ready. So one of the targeted things we were looking at was 100% heated and cooling by Mitsubishi Airsource VRF. The sole source of heat in this building. What was unique about this building was, everything was kind of changing inside and, they wanted a lot of future flexibility along with that. They had office rooms, they had, meeting and event spaces. So everything was kind of scattered and they had a cafeteria as well. So looking at this design, we did want simultaneous heating and cooling, perfect application, a lot of unique zones that could use heat recovery to its advantage, as well as using cooling or heating in certain spaces. Cold climate, Worcester's design considerations or temperatures for the winter time is around 0 or 2, according to ASHRAE. So we have to look at that, make sure we're going to be able to get the heating capacity that we need, which resulted in, low ambient condensers. Then also we had a little challenge with using refrigerant to water heat exchanger. The cafeteria, which is actually right here in this glass building, stood 2 floors tall. It was going to be tough to get some heating capacity over there. So what we decided to do is connect these hex units or, water heat exchangers. So it's refrigerant going from the condenser to these hex units, and they were, exchanging heat to a water loop. And this water loop was, a low temp hot water that was giving off radiant heat to that cafeteria space. Now, the cafeteria space also had, an air handling unit on the 2nd floor. So basically, these systems through controls were, not fighting against each other, and, one was on or the other was on, and we made it work that way. But, one thing that we had to use was a full building automation system with VRF to achieve certain functions, especially achieve, the energy, efficiency that we needed to achieve in the space to get to the net zero point. So one of the challenges was future flexibility required. This was an alumni center, and they said, we want a lot of zones right now, individual zones, but 5 years from now, we might want to change it up. So maybe want to take down a couple walls and make it into a larger conference room if that's what we need. So what we're able to do is kind of micro zone the systems, and if there ever a case where you did want to combine multiple rooms into more of a conference room setting, you're able to do that and actually group those fan coils together to form one zone, so it would stay in that mode on the controller basically. And then mixed use space, there was a lot of different fan coils that were added to figure out exactly what worked best in the space as far as aesthetic. So we used ducted units, we used 1-way cassettes, we used 4-way ceiling cassettes. So basically used all the fan coils to fit the needs in that space. And also one of the challenges was small zones with individual control. So we really needed to zone this building. In a lot of cases, if you had like a VAV system, the amount of zones we did would have not worked whatsoever. It would have actually been very expensive. And that's kind of why we went with VRF, because, believe it or not, VRF was a cheaper alternative for, putting in all these small zones for these small exterior office spaces. And then one of the other challenges was sustainability and net zero goal. They didn't actually quite meet net zero. The reason why they didn't is because there's actually 2 buildings. The Alumni Center, which, Mitsubishi had worked on, and then there's also a parking garage. And at the time, they kind of held off the parking garage and because they're actually supposed to place solar panels on top of the roof of the parking garage. Haven't gotten around to it. So I think that is an upcoming plan to make it closer to that, net zero goal. but that was really the only thing that was holding me back. And then lastly, you know, extreme weather, cold climate, I mentioned it was around 0 degrees. So, you know, we did need to use a low ambient heating condenser, which was rated down to, you know, negative 13 degrees to produce cooling heating capacity down to, you know, negative 25. And then cold climate accessories, we talked about this before. We need those stands, get them up 18 inches off the ground, and then your hail guards and snow hoods for protection, basically, through the elements. So this is a floor layout of one of the, I forget what floor this is, but this is a layout. Looks like the second floor, and just kind of showing you how, you know, micro zoned these systems are. All these exterior office spaces. You have a ducted unit feeding a conference room, another ducted unit feeding a conference room, and then you have some cassettes scattered throughout. So one thing the architect looked at was, yeah, net zero potential, and hey, how are we going to be able to achieve that? So Airsource VRF was compared with geothermal heat pumps. And, you know, as we were going through the process of comparing it, it did actually look like geothermal was going to give us about a 5% efficiency increase. However, in the Worcester area and the cost of, you know, designing and drilling wells probably would have added about 40% cost onto this project. So kind of right then and there, we decided that, you know, Airsource VRF was definitely the best approach. Even though it was a little less efficient, you know, it's still going to be efficient, and it still will provide us, you know, that net zero potential. And something that was cool about this project is we added some advanced controls for energy savings. So we added window switches. As soon as that window opened, basically it would shut off the ventilation, it would shut off the fan cooling unit. You know, occupancy sensors are actually located at one of these smart controllers right here. So, you know, if it wasn't occupied, then it would shut off your fan cooling unit and your ventilation as well. And the ventilation controlled by the room, so that was controlled by the local controller. What was cool that we added on was actually an enthalpy sensor outside of like an office space. And there's actually a green light associated with that sensor. So at certain times, it would say, all right, it actually makes, it's in favor of, you know, not running the HVAC system. Maybe we're 10 degrees cooler outside, and why don't we just open up the windows? So that green light would actually tell you in practice to open up your windows, which, you know, that window switch would then shut off all the rest. And that's kind of how it was made, and it worked. I mean, a lot of energy savings were shown from that. So this is one of these projects that applied for DOER grants and National Grid utility incentives. So we ended up getting around, I believe, like $50,000 to $100,000 for this project for energy savings. But one of the things that needed to be done through, you know, controls was trend hour intervals to confirm the VRF system matched exactly what the pre-design energy model was, to match exactly how it was operating. You know, we did that throughout the course of a couple months, and we decided that the grants would pass, and it kind of went through. So pretty cool project, you know, able to use simultaneous to our advantage, you know, flexibility along with it, and, you know, provide low ambient heating capabilities without any backup heat whatsoever. So yeah, this would be Clark University Alumni Center. And I think we have one more. I'm going to pass this off to Adam, and he's going to be talking about this one.
Yep, awesome. Thanks, Jason. So looking at this Wanna-Lancet Mills project we worked on up in Lowell, Mass. So this was a large retrofit project we did up there. And I'll touch on all sorts of aspects of the project, from how we decided to go with VRF and air source heat pumps to the final install, the equipment, and some images of that. So also, if any of you have ever been to Lowell around Christmas time, this building is right next to the large Christmas tree that they light up over there. So you can actually see those the lights in that image there, and I'll actually show another image of it in the nighttime. So moving on to the next slide here to just give a background of the. Sorry, Jason, if you don't mind skipping the. Yes, thank you. So to just give a background of the property, this was an old 19th century textile mill in Lowell. It's around 283,000 square feet. It has a nice exposed brick, wooden beams and oversized windows. They have office spaces on each floor with various different tenants, from Verizon to Coca-Cola and all sorts of other tenants. Then we also have large 10-foot ceilings throughout the building, which were a nice benefit of it being an old mill building. And then just going through some pictures here, I'll just skim through these quick. This next picture is just shows you a visual of the outside of the building, and then this small little river running by that branches off the Merrimack River. We can skip through that quickly. And then, as I mentioned, if any of you have been to Lowell during the Christmas time, you may have likely seen this large Christmas tree looking light arrangement that they put on. It's just outside where this historic building is. So moving on to give a bit of an intro to the property. Now, looking at what we faced initially when we were brought into the project, there were originally 21 very old DX air handlers, all around 4,000 CFM, so pretty big units. There were then gas furnaces for each system inside the duct downstream of the air handling units to handle the heating. So these units were having all sorts of issues with compressors failing and limited cooling capacity, with the equipment being towards the end of their usable life. So the owners knew they needed a new system. So also all of the air handlers were located in mechanical spaces on each floor and would have supply ductwork to each space from there. These actually use the entire mechanical space as a plenum originally, and then just use one large return grill to pull the air back into the return. So with the units being located in the mechanical room, there would be little disruption to tenants in improving the system and coming up with a new system. These also had the condensing section of the air handlers in that mechanical space as well that was ducted to the outside. So you'd have the ductwork for the space air, then the ductwork for the condenser section of the air handler as well, which made the mechanical space pretty packed. So they of course were looking to replace the existing equipment, as I mentioned, and ask the question that continues to come up very often, which is how do I electrify the building, or how could they heat their building without gas? So they looked at a few different options as new systems. One of them was a full condenser water loop with a dedicated water source heat pumps for each zone. With this system, you would need an electric or even gas boiler to moderate the water temperature in the winter, and then a dry cooler or a cooling tower to moderate the water temperature in the summer. So with this, you would need an entire hydronic piping network to be installed, along with the additional pumps to move that water around. So they were also looking at simple on-off water source heat pumps, which were not that efficient compared to variable speed VRF systems. So the next option, and the option, of course, which went forward, and what we're here to talk about today is for the VRF systems. So the alternative to that entire water loop with water source heat pumps was to provide VRF air handlers tied to the fully inverter variable speed VRF condensing units. So with this building, we have single zone systems with long ductwork runs and large capacity units. So what Jason touched on, we have our standard off the shelf VRF indoor units that can easily tie to the VRF condensing units. The only thing is that with these, we're limited by tonnage and by static on the fans to push the air to the space. So the largest standard VRF indoor unit is an 8-ton horizontal ducted unit, which is limited to around an inch of static, which Jason mentioned. So what we needed here for each zone was around 12 to 14 tons, which was outside of the standard VRF indoor unit range. And we also needed around 2 to 3 inches of static. So again, long duct runs. And then we also wanted to reuse some of the existing ductwork. So what we did was we used a semi-custom air handler and added a VRF coil and VRF expansion valve to allow it to connect to a VRF condensing unit. So all these, the VRF condensing unit, the VRF expansion valve, and the coil all need to talk together and to be sized accordingly to ensure you have the correct coil capacities, coil internal volumes, to ensure we stay at those correct pressures and temperatures, which we already spoke about. So this is a nice case study, as we're not just talking about a standard VRF project, but a bit of a unique scenario as an older building with specific design requirements that pushed us towards VRF tied to these semi-custom air handling units, opposed to just off-the-shelf standard VRF indoor units. And then also, each air handler does have a dedicated condensing unit. So we do not have one condensed unit serve multiple tenants. I think this is likely something we could have done, but I think the separate condensed units per tenant just made it easier for the owner to meter the electricity. So the question might come up about why we did not just use simple single or two-stage condensed units opposed to VRF. But as we've already spoke about all the efficiency benefits of VRF, along with the low ambient heating capabilities, which made for VRF really the go-to system for this one. And then also the Historic Association didn't want anything too tall obstructing the view at the top of the building, which as you can see by that Christmas light picture, we try to keep the visual clear for that. And then comparing the height of a cooling tower versus VRF condensed units, the VRF condensed units would be much smaller, which was another reason to push the VRF route here. Moving on, I don't think I mentioned, but we removed all of the gas heating there in the ductwork as well. So all the heating and cooling for the spaces is being handled by the VRF condensed units. So to bring in the outdoor air to the space, we're ducting that directly to the back of the air handling units. So when doing this, like Jason mentioned, you need to consider the mixed air temperatures on the coil. So we have limits to the entering air temperatures on the coils to ensure we have adequate and comfortable leaving temperatures. So with standard VRF indoor units, the coils are already sized for this, but in these more custom applications with semi-custom air handlers, with VRF coils, we have to make sure that coil is sized for the correct capacity and correct temperature rise. And then we've also, we have motorized dampers tied to the fresh air ducts. So the air handlers are only pulling in that OA during occupied hours when there are occupants in the zone, opposed to adding load to the coil when it's really not necessary to handle that outdoor air. And then with this all electric approach, we had utility rebates through National Grid and Mass EC. Rebates were awarded for the second phase of this, which consists of another, I think it was around 30 units as well. So we completed the first phase of this back in 2018, and it's been running great ever since then. In terms of the overall piping design, we have 4 risers or stacks of VRF air handlers on this 5-story building, with 1 riser going all the way down to the basement. So to make it simple during the install, we replaced 1 riser at a time to reduce the downtime and interruption of the tenants that were still in there while making these modifications. Then we would run some temporary fans to just keep the air moving during any downtime as well. So with these semi-custom air handlers, you have all sorts of options for cabinet sizes and configurations. So we're able to design them to ship in 2 pieces to fit through existing doors, making it for a simple install. I also touched on the more custom coils that we selected and used for these. These were actually field installed in the air handling units as well. There are now all sorts of options to get these done in the factory, which makes for easier integration for the installing contractor on site. So looking here at a comparison between the water source heat pump design versus the VRF design and what we looked at for the owner. On the left, of course, is the water source heat pump design, showing the cooling tower on the roof with the hydronic piping to each floor, then the boiler in the basement as well. So with these systems, you would also have a compressor in each space, which each mechanical space, which does add some noise. Also, you need to account for the additional pumps to move that water around. So looking at the water distribution, the piping is pretty big, with some around, I think, 4 inches and 6 inches piping to each water source heat pump on the floors. And then with the water source heat pump design, the entire hydronic infrastructure would have need to be installed before operating just 1 unit. So whereas the VRF units would just need the piping from the 1 condensed unit down to that air handler, and then it could be turned on. So with us breaking up the 21 systems into those different risers as well, we could just install those systems for each tenant to avoid disrupting the entire building all at once. And then just talking about the alternative VRF on the right here, with each piping shown from the condensed units on the roof down to each air handler. So as I mentioned, each air handler would have a dedicated 2 pipes from 1 condensing unit. And then these pipes are around 1 inch in diameter, which I'll actually touch on the next slide. So pretty small shaft space is required to fit all these. I think it was around 8 inches by 2 feet, the shaft space we used to fit all the pipes. I actually show a visual of this as well in the next few slides. So really pretty simple. And with this VRF design, we didn't need those additional components like the boiler, pumps, and cooling tower, like that water source heat pump design. So looking again here, this is a pretty typical VRF piping schematic that most manufacturers have out of their software, just showing the liquid and suction gas line from the condensing unit, which is labeled CU1 there, to the air handler in each space. So as I mentioned, you can see that the piping is 1 1/8 and 5/8. So pretty small pipes for these large capacity air handlers. As I mentioned, I think they were 12 to 14 tons, which is pretty easy. Now, looking at the floor plan and showing a visual of the ductwork configuration, I'll just skim through this quick. You can see the large duct runs, which would mean there's a lot of static for the fans to push against. So this is why we could not just use any off-the-shelf VRF indoor unit that has that limit on the amount of static. So with these semi-custom air handlers, we can size the fans accordingly and ensure we can push the air through all that ductwork. And then just looking at a final install pic here of the air handlers with these VRF integration kits, you can see on the right here, or kind of in the middle, we have the expansion valve that was field installed. And as I mentioned, you can now get these factory installed as well. You can see the piping going in and out of it. Then we have the variable frequency drive, or the VFD on the fans to modulate the airflow to the space. On the right there, you can see those refrigerant risers that I touched on, and you can see the insulation on those as well. I believe this was on one of the upper floors, showing all the pipes feeding the units below. But as you can see, the shaft space required is still pretty small with these pipes. And then also there's that small white PVC piping, which is for the condensate dripping off that coil when it's operating and cooling. So here's just another visual of the HU, or the air handling unit. This is prior to the VRF expansion valve and piping being installed, just showing that modular semi-custom air handler that was designed to fit within the space, while also being able to fit within the doorways to get into the mechanical room as well. Now, looking at the condenser units on the roof, we always suggest elevating the units at least 18 inches off the ground, like Jason mentioned, in our climate to just keep them above the snow line. So there are a few different options to do that. One being just off-the-shelf stands, which you might have seen before, that need to be bolted into the roof. So these come in set sizes that are to fit each different manufacturer's condenser unit. There are also non-penetrative versions of this, which need to be pre-engineered to withstand a specific wind rating. We've ran into a few different projects where we went with these, as you couldn't fix the alternative stands into the roof. You just need to make sure those are always designed properly in advance and correctly specified as well. The other alternative, and what we went with here, are condenser unit rails, which make for a pretty clean install, especially with long rows of condenser units like you can see here on the right. These can still be used even if you have just 1 or 2 units as well, which we've also done in the past. As you can see, it looks pretty clean and simple. So one other point on this is the small black neoprene pads that you can see in the left picture there. So those are used as additional isolation on the units, as we are always asked by engineers or owners about vibration and isolation. So we typically try to push away from that, as firstly, most manufacturers' condenser units are all internally isolated. And then secondly, we often have a hard copper piping from our condenser units, which means any slight movement from springs could possibly cause shearing in the piping. So if any extra isolation is needed, we typically would like to go with these small neoprene pads, which we used on this job, and the condenser units just sit on those, which is pretty simple. So these next 2 slides here are pretty, I'm just going to skim through these pretty quickly. This is just showing the condenser unit being craned onto the roof and mounted onto the rails, like I just spoke about, and mounted onto those neoprene pads. And then this last pic here, just showing the final install, which as you can see looks pretty clean with that beautiful Christmas light in the background, and just the units mounted on the rails, all evenly spaced apart. So lastly, just to summarize everything that I just went over here, and comparing the 2 options we looked at, the VRF versus the conventional water source heat pumps. Firstly, comparing the energy efficiency side, we looked at simple on-off water source heat pumps. So as you can see there was a big operational cost savings with going with the VRF for the good part load efficiencies we've already spoke about. The downtime for the tenants in going with one water loop that would need to be up and running prior to operating any of the water source heat pumps. So this, of course, would add significant downtime to not have to have proper heating or cooling system rather than just using temp heat or temporary fans. So that was a big deal with going the VRF route. And then with all the incentives nowadays for going all electric, the capital cost of the VRF system allows for short payback and lower lifetime cost of the system. Then just comparing a few additional things with the VRF systems that have the variable speed operation, which improves the occupant comfort versus those on-off water source heat pumps, which could easily overcool or overheat the space, which is what Jason went over. With them being a single stage system as well, it could mean that they would be turning off and on more frequently, which would be inefficient. And then reduce maintenance on the VRF systems without the need to maintain the water loop, which would need strainers, chemical treatment for the water, and pumps and all things like that. We've also actually had the maintenance staff all trained up on the VRF systems, and even had one of the VRF central controllers, which we touched on. I had one of those installed, which allows them to remote access into the system and then do any sorts of things like programming for schedules or set points, and then also helping with diagnosing issues. And then, as I mentioned, the owner was pretty happy with the solution, and we've even gone forward with another 30 units in other parts of the building. So I think that's everything we have for today. We're going to jump into the Q&A portion.
Yeah, if anyone's got any questions, we're going to stick around for the remainder of the time, the next 20 minutes. So feel free to ask away.
I just want to make sure people realize that there are a lot of questions that have already been answered in writing in the Q&A. So if you have additional questions, you can either type them in there or you can raise your hand, and then I think we can unmute you.
I just want to address Robert Zog's question there, asking about why is a cooling tower needed for the water source heat pump option with the cold canal water available to reject heat. I think that they didn't want to look into that whole infrastructure of providing the heat exchanger for that canal. I assume that I think there's all sorts of different ratings for those heat exchangers, which would add quite a bit of costs. So I think they were just looking at using a cooling tower instead.
And if anyone doesn't have any more questions, again, we're going to be around a little longer, but just wanted to say thank you all for attending today and talking about heat pumps with us. And hopefully you got something out of it.
Yeah, thanks to Adam and Jason for giving a great presentation, and to Brian for help with all of the Zoom stuff. And again, I'll be sending out the CEU information and slides later on. Looks like we do have, oh. I just answered that.